In this video, we're going to talk about correlation. Correlation happens when you have a linear association between two quantitative variables. We call it R, correlation R, or a correlation coefficient, if you are feeling so fancy. It measures the direction and strength of that association. So, a couple of facts. There's going to be a lot of facts about correlation in this video, so get your writing fingers ready. I don't know. Correlation is always a number between -1 and 1. So it can be -1 and it can be 1 and any number in between. It indicates the direction of a linear relationship, as we said. So if R is greater than 0, that's a positive association. And if it's less than 0, it's a negative association. For those extreme values, so that R equals -1 and R equals 1, those occur very rarely and only in the case of a perfect linear relationships, when the points lie exactly along a straight line. So that is a really wicked strong correlation. So if the linear relationship is strong, the correlation R will be close to 1 or -1. And if it's weak, the correlation R will be close to 0. And that could be on the negative or the positive end. So it is only appropriate to use correlation to describe strength and direction for a linear relationship, which is why the word linear kept appearing in the list above. And here we have a whole bunch of examples of what correlation could look like and what the correlation coefficient, or R, could be for these graphs. So looking at this one up here, we've got R equals 0. Remember, that is not a strong relationship whatsoever. That is a very weak correlation. Couldn't really draw a line any which way through those dots. And then we've got -0.3 here. Less weak, but definitely still weak. Can't really draw a great line of best fit through that. Then we've got 0.5, which is starting to develop into a line. It's not weak, but it's not necessarily strong. It's moderate at best. And then we've got -0.7 over here, starting to develop into more of a line of best fit. We've got 0.9, that's getting way closer to a stronger relationship. We've got, I could draw a line through that. Yeah. And then we've got -0.99, which is ridiculously close to -1. So that would be a really strong correlation. And we could draw a line right through that. Also note that for anything that you could draw a line through, so for example, this -0.99, that's a negative slope. That would be a negative slope, so that makes sense that we have a negative R value. And this one is positive, so we would have a positive slope there. So let's look at an example. This one's called Payroll and Wins. So if you think back to that MLB data from 2016, where there was the payroll data in millions for 30 teams and then the outcome of their games, so number of wins. Here's the scatter plot showing the relationship between payroll, millions of dollars, and wins for MLB teams in 2016. That data says that our R value is 0.613. Let's interpret the value of R. Also, something to note when you are answering questions like this or describing relationships or trying to find correlation, always include context by using the variable names in your answer. So what I see here is that things look kind of positive, so that positive R value makes sense, and I could probably draw a line of best fit through there. It won't be like R equals 1, but it's relatively close. So we would say that this is moderately strong and definitely positive. So we could say something like the correlation of R equals 0.613 confirms that the linear association, linear, between payroll and number of wins is moderately strong and positive. So we know that correlation is a great way to measure a linear relationship between strength and direction, but it's kind of finicky. It's got some limitations. It can't do everything. It's not a panacea for all of your statistic woes. So I'm going to share with you a couple of cautions about correlation. First up, correlation does not imply causation. You might have two quantitative variables that are very obviously linked, but that doesn't necessarily mean that changes in one of those variables is likely to cause a change in the other variable. Look at this example. This one is about data points of revenue from skiing. So we've got ski lodges, skiing facilities in the United States. And then they also collected information about the number of deaths of tangling in your bed sheets. So there's a very, very strong positive linear relationship here. But that doesn't mean that revenue and tangling in your bed sheets has anything to do with one another. One doesn't cause the other. I hope not. Let's hope not. Our second caution is that correlation does not measure form. Remember, it measures direction and strength. Definitely not form. So what we have here is a comparison of a motorcycle speed and the braking distance in feet. Now, this association is curved, not linear, and it has a high correlation. So correlation does not immediately indicate that you're going to have a linear relationship, right? Because that's a curve and it has a high correlation. So it does not measure form. And that brings me to my third caution, and that is correlation should only be used to describe linear relationships. Correlation doesn't measure the strength of nonlinear relationships. So we've got a curve here. Very, very clearly that's a curve and not a line. And, the correlation is 0. It's weak because it's not a line. And our fourth caution is that correlation is not a resistant measure of strength. Take a look at this example here. We've got a pretty loose cluster, we'll call it a cluster, of points over here. We've got an outlier. So if I found the correlation coefficient, or R, I would get negative 0.13 with this outlier. But if I removed this outlier, my R value becomes 0.72. So that would tell me that correlation can be greatly influenced by outliers. Let's take those cautions into consideration and work through an example. This one's called Nobel chocolate. The problem says most people love chocolate for its great taste, myself included. But does it also make you smarter? Oh, I hope so. A scatter plot like this one recently appeared in the New England Journal of Medicine. The explanatory variable, down here, is the chocolate consumption per person for a sample of countries. The response variable is the number of Nobel Prizes per 10 million residents of that country. So all of these dots are labeled with their country name, so you can check this out. And our R is 0.791, so that's pretty strong. So let's take a look at this first question. If people in the United States started eating more chocolate, could we expect more Nobel Prizes to be awarded to the residents of the United States? Explain. So first things first, here's the United States. Here's our dot right here. So we've got chocolate consumption is a little more than 5 kilograms per year per person. And then over here, we've got maybe 12 Nobel laureates per 10 million people. So I don't think you need this graph to really answer this question. I don't think if more people started eating chocolate that we would have Nobel Prize winners, more of them in our country. I just don't think so. So let's figure out how to explain that using statistical language. So here's what we could say. The answer is no. We know that. Even though there's a strong positive correlation between chocolate consumption and Nobel laureates in a country, causation should not be inferred, right? That was our first caution. It's possible that both variables are changing, the chocolate consumption and Nobel laureates in a country. They're both changing due to other variables like per capita income or years of education. And the second part of this problem asks us to figure out what effect Switzerland has on the correlation. So here's where Switzerland is, and there's where the United States is. Woo! Switzerland, people eat a lot of chocolate, maybe like 12 kilograms per year per person. All right. And, they've got a lot more Nobel laureates per 10 million people. Almost 35. That's a whole bunch. So what effect does Switzerland have on this correlation? Well, Switzerland's out here, and it definitely lines up with whatever kind of line we might have here. So Switzerland definitely adds to this strong positive correlation. Here's how we can say that a little more eloquently. When Switzerland is included with the rest of the points, it makes the association stronger because it doesn't vary much from the linear pattern happening. This makes the correlation closer to 1. Now you may be wondering, how on earth do we get this correlation R value? Well, you can calculate it algebraically. It's super fun, super easy to understand. Totally kidding. Let's look at it, and then don't worry, I will show you how to find this on your calculator. Okay, so this is a whole big equation that they've boiled down to here. So this is what your calculator is doing. So here's what we got. Remember that we have two quantitative variables. Doesn't matter which is x, which is y, doesn't matter. And we have some number of individuals, right? So if we surveyed 100 people, that'd be 100 individuals. So that is where n comes into play. So anytime you see an n right there and right there, that means number of individuals in your data set. So the values for the first individuals are x1 and y1, right? Doesn't matter which one is which. So you would have 1 over n minus 1. So 1 over, if that was 100, it would be 1 over 99, and then you would multiply each set of values. So you'd have your very first x value, and then you would subtract the x bar, which is our mean, and you would divide by the standard deviation for those x values. Then you would do the same thing with y and multiply them. You would take that one y value, subtract the mean of all the y values, and divide by the standard deviation of the y value. And you would do this, you'd add it to every other term like that. Isn't that fun? Oh my goodness. Whew. Yeah. Or you can take this addition, this summation, you still have that 1 over n minus 1 here, and you would just sum up the amount of terms minus your x bar over the standard deviation and do the same thing with y and multiply them together. Or you could use your calculator. So let's take a moment and walk through this. So let's say I want to use that data on those 30 MLB teams in 2016 and their payroll in millions and their wins that they had over that season. So first thing you want to do is enter that list, right? You go to stat, you go to edit, you type in those numbers, you double check them, right, that they're correct. And then the second thing you're going to want to do, and you can do this at any point, but you could do it before you enter the list or not. What you want to do is you want to turn something called a diagnostic on. And the way that I like to do it is I press second, so second and 0, and it brings up this thing called catalog. And you can page all the way down, because it starts with A, you can go all the way down to, diagnostic on, or you can find where there is a D. So if you've ever played around with the alpha mode, or you can write secret letters to your friend and pass it on your calculator. What? You haven't ever done that? What is wrong with you? Oh, right, you have texting. Never mind. You could press D or any letter in the catalog and it'll bring you down to the Ds, or you could just page down. It doesn't matter. But you go down to diagnostic on, you hit enter, and then it comes back to your calculator screen. You want to make sure you hit enter again. You want to make sure you turn it on. So if this comes up and this isn't there, where it says done, you haven't hit enter quite enough. So make sure diagnostic actually is turned on. So the third thing that we're actually going to calculate is something called a linear regression. And you may have seen that before if you've ever done work finding the line of best fit, which is essentially what we're trying to do here. Turning that diagnostic on will give us our R value, or correlation coefficient, which is very handy. Your calculator might already have that function on. You may have seen this before, so hey, you're already finding R values. Look at that. So anyway, how you do that is you hit stat, you page over to the calc menu, you pick linreg, the ax plus b form, that's the first linreg that shows up, you hit calculate. My screen looks like this. If you have an older operating system, it might look slightly different, but essentially you put your x list, your y list, use vars if you need to change those. You don't need a frequency list. You can store the equation. That's when you go to vars and you pick y1, and then you hit calculate. So this is the linear regression equation. That would be the line of best fit through those 30 MLB teams, all that data. But here is our R value, our correlation coefficient. So that's about 0.615. So moderately strong and definitely positive. For that data set at least. So now that you've put your calculator down, let's talk about a few more things about correlation. Some of these things we've seen already, so not all of this is brand new. But anyway, let's jump in. 4 big points. So when you have two quantitative variables, you can find correlation, but they must both be quantitative. So if one or both of them are categorical instead of quantitative, that's an association, not correlation. Number 2 is that correlation makes no distinction between explanatory and response variables. The x and y doesn't matter. And R does not change when units of measurement of X and or Y change. So if you measured those ball players in centimeters instead of inches or feet, your R value wouldn't change. And correlation R has no unit of measurement. It's just a number. So now let's do one last example about long strides. So the problem says the following scatter plot shows the height in inches and the number of steps needed for a random sample of 36 students to walk the length of a school hallway. The correlation is R is equal to negative 0.632. So here's our scatter plot. We're going to answer 3 different things about this scatter plot. First thing we're asked to do is explain why it isn't correct to say that the correlation is negative 0.632 steps per inch. Well, if you paid attention 2 slides ago, we know that R is just a number. So we would say, because correlation is calculated using standardized values, it doesn't have any units. So it's just R equals. The second thing we're asked is, what would happen to the correlation if number of steps was used as the explanatory variable and height was used as the response variable? Meaning, essentially, that you swap height and number of steps. So height would be over here and number of steps would be right there. Once again, a couple slides ago, we know that the correlation would be the same because correlation doesn't make a distinction between explanatory and response variables. So height could go up here, a number of steps could be down here, your R value stays the same. Last question we're going to answer in this video, I promise. So, what would happen to the correlation if height was measured in centimeters instead of inches? So just like the last question, correlation would be the same. Because R is calculated using standardized values, changes of units don't affect correlation. So, if you measure that in anything other than inches, your R value would stay the same. Now that's going to do it for this video. Thank you for watching.